All right, so let's go ahead and continue here the review. We're now looking at section 2.2, and section 2.2 is essentially dealing with the intramolecular forces. And potential energy. So I'm just going to abbreviate that as PE. Now, the main thing to walk away from this is really a couple of items. One, if we're having these intramolecular forces, remember the intra means that these are going to be bonding or interactions occurring within the molecule itself. Okay, and so these forces are essentially the bonds occurring within that. So you have a molecule. We're wanting to see how strong these atoms are being held together. And also it's a matter of how long the bond is between the atoms. So again, if we go back to that general example here and we look at the atoms, and so let's say that I had an atom 1 and I had another atom 2, we're going to have that interaction here. I'm just going to represent that bond as a green line here. Essentially, we want to make sure that we understand that some atoms, draw a second set over here, say I'm going to have an atom 3 bonded to another atom over here. Just to distinguish here, I'm going to give it a different color bond, put it a blue. And so the idea here is if you look at the two atoms, specifically atom 1 and atom 2, and if we look at the length between the atoms here represented by the green line, the longer the line, essentially that means that the greater the distance between the two atoms. Now, if atoms are far apart from each other when the bond is formed, that essentially means that the force of attraction between these two atoms is actually relatively weak in comparison to, say, another bond. And so I've got another bond here with atom number 3, atom number 4. Notice the length of atom 3 bonded to atom 4, that particular bond here represented in blue is significantly smaller in length than the bond represented over here between atom 1 and 2. So what we would say between these two atoms is that the bond over here, I'm going to put this here as a line, this is going to be a weaker bond. Largely because here the length is longer. And I'll explain here because it's related to Coulomb's law, and we got to make sure we take that into consideration. And then this other bond over here at the bottom, we say here, this because this one is shorter, this is going to be a stronger bond. And again here, because the length is shorter. Now, why is this important? It's very important because what we have to consider here is Coulomb's law. Now, Coulomb's law is a major thing that we use to determine the forces of attraction. You would have seen this in two different versions, but I'll use the one here in this one. It's essentially a Coulomb C, and this is essentially representing the force of attraction, is going to be equal to a constant, a Coulombic constant, K, and then a value of Q1, Q2, and this is going to be over the radius squared. So the idea here is if this bond here, R, has a smaller length, we can represent that as R, essentially. But here when we do the radius, it'll be the radius from center of the atom to center of the atom, and then that's what that value there is. And the same thing on the other atom, R is here. Since the bond between atom 3 and 4 is significantly smaller, you want to consider that what that means here in the equation, because the smaller the value of R here essentially is going to give you an overall smaller value down below in the denominator. So when you plug all the other numbers in here into the equation, you're going to get a very high Coulombic force. So smaller bond lengths are associated with stronger bonds between atoms. So that's a very crucial thing to know. The other item that you want to know in this general section, and so let me just kind of get these here. Let me go back a little bit. Okay, let's go ahead and move this over here to the side. We'll come back to that in a little bit. Now, the other item here is a couple of items. So we need to talk about the strength. So when we said strength earlier, what we're really referring to here is the bond energy. Okay, and so that's that number that we looked at here with Coulomb's law. And so there's a way that you can figure out which is a stronger bond. And so that means that we have to look at things like bond order. Okay, so versus bond order. And so here bond order is referring specifically to whether you have a single bond, a double bond, or a triple bond occurring between atoms. And so the weakest of them is the single bond, and the strongest is the triple bond. And so here you can see, by knowing the bond order, and you can literally just look at the compound or the molecule and you can see, oh, look at this particular bond between this atom and that atom. Well, that one looks like a single bond. Well, then you know that the energy associated with that based on Coulomb's law is a lot lower. Okay. And then you also know based on radius, if you can't figure it out based on the actual bond type, you can actually, if they provide you information on the length, maybe in picometers or some other kind of unit of measurement for length, the bigger the number obviously is going to mean that it has a longer distance or a bigger value of R, and that would mean that the length is greater. So when you plug it into that Coulomb's law equation that we looked at just previously, that will tell you that the bond energy associated with those is going to be a lot lower for longer separated atoms. And so one of the things here with the bond energy is that you can actually see that as the bond energy goes up, that's largely because what we see here is that those atoms are going to be stronger bonded. Now, bond energy can vary even at the single bond level, and so obviously some single bonds are stronger than other single bonds, and that has a lot to do with electronegativity between the atoms. So you want to pay attention to those kinds of things. And so just to summarize here, the bond energy essentially is, if the bond energy goes up, essentially this is essentially congruent with stronger, and the bond energy goes down, this is essentially congruent with weaker. And so all of these items here are also tied into this idea or notion of bond order. Both of these can go hand in hand, and you can use both to your advantage and to figure things out. Another item that you needed to know about in this section is going to be the concept of this potential energy curve. And so in class we had talked about this curve, and so that curve essentially kind of looks like this. You've got a drawing like this, and then you've got a curve in here, kind of looks something like this, and approaches there. And so I would be very familiar as to what is happening up here, say at position, let's call this position 1, position 2, and then what's happening here, maybe just to distinguish, maybe here position 3, and then over here at the very top, position 4. And so typically the general example, as we shared in class, is you've got a couple of atoms here. The traditional atom was hydrogen, but you can really have any atoms that are engaging in some kind of interaction with each other. And so let's go ahead and move back. And so idea here at position 1, so the atoms here are far apart. And so the interaction here is essentially weak. Weak to no interaction at all. I'll abbreviate that there as interaction there with a hyphen. Now at position 2, this is the cool stuff, because at position 2, as those atoms approach each other, I'm going to generically kind of draw the atoms like this. The atoms are moving close to one another, but they're still far apart over here on this end. I'll share this here as in green for this one. The point down at the bottom, that particular point there essentially is marking the section here where the attractions is essentially balanced out with the repulsions. Now, be familiar with what those attractions are. Remember that the attractions that we're referring to here are the attractions occurring from the positive core of one atom to the electron of another, and vice versa. And then the repulsions that we're referring to here in this regard here are essentially the positive core of one atom to the positive core of the other, as well as the electrons of one atom versus the electrons of another atom. So just atom 2 here and then atom 1. That's what's occurring here. And when they're balanced and equal, this essentially is where we're going to see the bond formation. Okay. And so let's label that accordingly here. This essentially is going to be where the bond is formed in that area there. Okay. So that's very important that we distinguish that as we go through here. Now, anything past this point here, once you reach this point, this is essentially where the bond is formed, but anything closer over here, and I should probably label on this end here, this point over here is 0, and so potential energy increases. So this potential energy increases that way, and then on the scale here on the x-axis, length or distance it increases to the right. And so overall, though, once you move to the left of this particular point where the bond is, you're going to see here that the repulsions increase. So at this point, you've got greater repulsions than you do attractions, but still the quantity here is pretty low. Once you cross the barrier at 0, those repulsions essentially get very high, and those atoms are going to be want to separate as fast as possible. And so because there's a huge amount of repulsions, in order to keep them together like that, there has to be a certain amount of energy that needs to be inputted into the system to keep them like that. But the natural order of things is going to be that they're going to separate. And so this is going to be very important for us when we do that. The other item for you that you need to be aware of is what happens to this curve. If I've got this curve, will this curve shift? If it does, and just remember that a certain length here is going to be dependent on size. Again, tying back into Coulomb's law, that the bigger the atom, the lower or the smaller the bond energy, which means that the requirement will actually be a little bit lower. So if you've got big atoms, you could expect that dip to be a little bit lower overall, and so that'd be represented by blue, the blue curve here. So notice that there was a shift up from the bottom here. It shifted up. Now, if you're having, for example, here in terms of the bond length, we also have to keep in mind that this particular curve is going to want to, the blue line is actually going to be shifted just a little bit over to the, not only up, but you're also going to see that that particular length is going to be shifted to the right. So if I'm going to correct this, let me go ahead and do that now. Because I want to make sure I get this correct here. Let's go ahead and draw that again. So big atoms here with big bond lengths essentially are going to be shifted over to the, like this, up. And so notice you can see the shifting here. It actually went up from this level, it shifted up, but then it also shifted to the right, indicating that. You should also be aware of what happens if it shifts further down. So let me draw that in a slightly different color. I'll draw it in purple. If you've got two atoms, for example, they're very small, say like 2 fluorine atoms or 2 hydrogen atoms is kind of good here, but say like 2 fluorine atoms, very high electronegativity, you can see that that bond curve is actually going to go pretty, let me draw it a little bit better. It'll be actually a little bit shifted to the left. It'll be dramatically down, and then you have it come up. I know I didn't draw that straight, but you can see here the purple curve essentially indicates that the bond length decreased, and there was a huge drop in energy because there's a lot of energy that was released when those 2 electronegative atoms were bonded together. And so those are 2 of the main things that you need to be worried here in Unit 2.2. And so just keep that in mind as you kind of go through. Oh, yeah, and the last thing here is when you do release the energy, because this curve actually just drops down below 0, keep in mind that all of these, the yellow below the 0 curve, the same thing for the blue, and the same thing for the purple here. Anything below this 0 line essentially is going to be a release of energy, which is exothermic. If you ever see a line above the 0 axis here, then essentially that would be a line that requires energy to input. So you can see that above the line here, at these points here for the purple, at these points here for the yellow, and these points here for the blue, all of those indicate endothermic scenarios where energy needs to be applied. But over here below the line for each of these blue, yellow, and purple, you're going to see that all of these are exothermic, each reaching the height at the bottom of each respective curve. Okay. And so that's the main thing to keep in mind there. Right. So I think those are the highlights here for Unit Section 2.2. I'm going to go ahead and end the video here. I'll go on to 2.3 in the next video.